Okay, so time for another example. I'm sorry I always start off screen. I'm waiting to make sure that it's actually recording so that I don't stand in front of a camera that's not on and just jabber away. But that means I'm always going to start off screen. Kind of weird. I'm kind of weird. Deal. Okay, new problem. We want to find the surface area of the part of the paraboloid z equals x squared plus y squared minus 1 that lies below the xy plane. So, that's just my standard paraboloid, except it's been translated down 1 unit. So instead of having its vertex at the origin, its vertex is down here at 0, 0, negative 1. So that's what the paraboloid looks like. And of course, we're asked to find the surface area of just the part that lies below the xy plane. So the surface area of a little bowl-like shape, something like that. Okay. So, if I project this onto the xy plane to find what my region is that's the domain of this function, I basically am looking for where this thing intersects the xy plane, which would be where z is equal to 0. But if z is equal to 0, then x squared plus y squared is going to equal 1. So that's the curve that is the boundary for the region over which we're going to be integrating. And that's just the unit circle. So I can see we're going to be integrating over the unit disk. Whoops. That's the region D over which we'll be integrating. So again, this suggests that we might want to switch to polar eventually, but we need to get this set up first because the formula for surface area involves the partials with respect to x and y, not the partials with respect to r and theta. Okay, so if I look at this, the partial of z with respect to x is just 2x, and the partial of z with respect to y is just 2y. So I can say, okay, my surface area is going to be the double integral over d of the square root of 1 plus 2x quantity squared plus 2y quantity squared dA. So that's the double integral over d of the square root of 1 plus 4x squared plus 4y squared dA. Once it's set up, excellent time to switch to polar. So, if it's the unit disk, theta is going from 0 to 2 pi, r is going from 0 to 1. Notice that this right here is just 4 times the quantity x squared plus y squared. So what we're integrating is the square root of 1 plus 4r squared, but then my dA becomes an r dr d theta. I am often very happy when I get to switch to polar coordinates for a surface area integral, because the integrand is always going to be this square root. It was really nice in the first problem we did because we ended up getting just a constant, but if we don't get a constant, integrating square roots is often messy. When we switch to polar, we get this r on the outside, and often, as is the case here, that's going to enable us to do a u sub. So I'm going to let u equal 1 plus 4r squared, then du is 8r dr. I've got the r, I need an 8, so I'll introduce an 8 and counterbalance with a 1/8 on the outside, and then I can say this is 1/8, the integral from 0 to 2 pi. This inside integral with respect to r is where we're doing the u sub. So the u value at 0 is 1 plus 4 times 0 squared, that's going to become 1. The u value at 1 is 1 plus 4 times 1 squared, that's going to be 5. Okay. And then we've got the square root of u, which is just u to the 1/2, and then all of this here, the 8, the r, and the dr is my du. Once we've done that, we'll integrate with respect to theta. All right, so that's 1/8 integral from 0 to 2 pi, 2/3 u to the 3/2 evaluated between 5 and 1, and then we've got to integrate that with respect to theta. So that's, I'm going to pull out the 2/3, so the 2 can cancel with the 8, so it looks like I'm going to get 1/12. the integral from 0 to 2 pi of, let's see, when I plug in 5, I'm going to get 5 to the 3 halves minus 1 to any power is 1, and then we've got to integrate d theta. Excellent opportunity to remind you of my rule for simplifying exponential expressions like that. This means I'm taking the third power and the square root. If the root part is nice, I expect you to evaluate it. So if that had been 4 to the 3 halves, we'd be able to evaluate that. If the root part isn't nice, you can leave it as a fractional exponent. Okay, so I need some more space. So let's just copy what we had. We had 1/12, the integral from 0 to 2 pi, 5 to the 3 halves minus 1, d theta. There are no thetas in there. That's constant. It's kind of a funny looking constant, but it's a perfectly acceptable constant. When I'm integrating a constant, I just get that constant times the length of my interval. So I'm going to have 1/12 times 5 to the 3 halves minus 1 times the length of that interval is 2 pi. I can cancel the 2's. So we're going to have just pi over 6 times 5 to the 3 halves minus 1. That's going to be our surface area. Quick common sense check, that is a positive number. That is in fact a good thing. Okay, back for another example in a minute.